Next up, number 2 on our top 4 climate change timescales, we have the short timescales that are years to decades. One of the changes would be related to variability in the tropical ocean heat pump. The best known example of this would be El Nino La Nina cyclicity, also known as ENSO. And what we'll be talking about here for a minute or so, coming back to this during the next lecture series, is the sloshing back and forth of Pacific surface waters that are warm. During an El Nino event, warm water pools off the coast of South America. Generally, this happens around Christmas time. This is how it obtained its name, El Nino, the child, referring to the Christ child in this case, a name given to this phenomena by Portuguese fishermen around 500 years ago. In La Nina, the opposite scenario, the warm water pools off of the coast of Australia and throughout Indonesia. During these time periods, there's significant upwelling. Biological productivity is very high, whereas during El Nino, biological productivity comes to nearly a stop. Upwelling is cut off, and that upwelling, not being able to bring nutrients to the surface, squashes the whole food chain. Let's take a look here at El Nino over a period of years, starting in January of 2015. What you're going to see is some warm water depicted by these darker reddish colors pooling off the coast of South America. Ultimately, this is going to break down. This cap of warm water is going to be replaced by cold water via upwelling. And as it's displaced, it moves to the west towards Australia and Indonesia. Here we have the warm water approaching South America. It's pooling, cutting off upwelling, which cuts off the nutrients off the coast of South America, shutting down the herring fishery. Seals and seabirds disappear. Now the upwelling has begun in earnest. Lots of nutrients coming to the surface in this cold water, and the herring come back, the seabirds come back, the seals come back, and the fishermen come back. We'll get back to this again when we get to ocean circulation next week. Number 3, longer timescales. These are 1,000-year, multi-1,000-year timescales. Include changes in deep ocean circulation. Our best known example of an ocean current, at least from our perspective as North Americans, is the Gulf Stream. And you can see that transecting here from the Florida Straits past the east coast of the United States up to maritime Canada, ultimately splitting up around Iceland, becoming part of the North Atlantic Drift, ultimately getting entrained in the East Greenland Current after it submerges. Let's take a look at the Gulf Stream now, how it develops off the coast of Florida, and how it affects climate at the higher latitudes. Gulf Stream beginning in the Straits of Florida and transecting to the higher latitudes. This is going to influence all of the east coast of the United States and maritime Canada, as well as Northern Europe. But it has a global signature. Here we can see the Gulf Stream moving to the higher latitudes. The water is going to cool off. As it cools off, it becomes denser. It's already salty because it became salty off the coast of Florida and in the Caribbean. As this water sinks, it becomes part of the deep water mass that travels the world's ocean basins. Here's a schematic of the water increasing in salinity. It's cooling off at the higher latitudes. And this high density water sinks and then traverses the world's ocean basins. Number 4 in the time scale, the longest time scale, tens of millions of years to hundreds of millions of years. Our best examples are plate tectonics, or plate tectonic related. The best example of plate tectonic activity is the Himalayas, pictured here. Here we have a short video related to the origin of plate tectonics. These plates are ultimately moved either by push or by pull by the Earth's mantle. The mantle itself is driven by radioactive decay within the Earth. decay heats overlying material, decreasing its density, causing it to rise. Once that material cools, moving away from that hot origin, it sinks. This pulls plates apart. You can see that at the Earth's surface here in Iceland, a place called Tingfeller. Iceland itself is essentially a large volcano. Now when we move into continents, we smash two continents together with folding and faulting of the Earth's crust. With sufficient pressure, we can lift or elevate that crust, producing mountain ranges. Now, say off the coast of Southeast Asia, we have ocean-ocean plate collisions that generate very explosive volcanic eruptions. These explosive volcanic eruptions ultimately lead to the formation of the islands, such as the Philippines and Japan, and the generation of dangerous tsunamis. Okay, now we're going to step back a bit and look at the global imbalance of energy. Now, this imbalance that we touched upon recently is the reason that we have weather on Earth. It's also the reason we have different seasons on Earth. The atmosphere and the oceans are going to take excess energy supplied at and near the equator, redistribute it to higher latitudes via wind and water transport of heat. In this diagram, what we can see is a cross-section of the Earth. The sun would be located over here. As it's perpendicular to the surface of the Earth above the equator, the most intense radiation is going to be received here at the surface. This is about 2.5 times as much energy as is received at the poles. As we move higher in latitude in the northern hemisphere here, the angle of the Earth's surface changes relative to the sun, so that spreads out the incoming flux of radiation. It essentially reduces the flux at the Earth's surface. And by the time we get to the highest latitudes here near the North Pole, the Earth's surface is nearly parallel to the incoming radiation, therefore receiving a relatively low flux of incoming insolation. Now, the Earth has a way of compensating for this difference, sharing the wealth, one way to put it. It results in this kind of distribution of incoming radiation. Because of this, the global wind belts and the ocean currents are generated and maintained from year to year, season to season, millennia to millennia, because the tropics have and will continue to receive more insolation than the poles. So here we see a latitudinal scale on the bottom, the X scale, where we have the equator located right here. The maximum insolation is going to be obtained at the Earth's surface at the equator. As you move away from the equator, in the northern hemisphere to the right here, we're going to see a reduction in the amount of insolation as we saw in that last diagram. The net result is we have a net radiation surplus here at the low to almost mid-latitudes, and a net deficit beyond that to the higher latitudes. So we're taking this excess radiation, this net radiation surplus, and we're redistributing that radiation to the higher latitudes, to the north here and to the south here. We're doing this distribution, or this sharing of the wealth, the insolation, via heat transport as it's carried in wind, as it's carried in ocean currents, and importantly, as it's carried as latent heat. When we talk about incoming radiation, we also need to talk about diurnal variability in that incoming radiation. It's not steady from minute to minute throughout a given day. It varies quite considerably. So what we see here in this diagram is a day of the year somewhere in the northern or southern hemisphere in which the sun rises at 6 a.m. and sets at 6 p.m. This happens twice a year. I'll let you try to think about when that is, these two dates, no matter where you are latitudinally, if you're in the Caribbean, or if you're in none of it, it's going to be the same day of the year. Which day is that? And then it happens again later in the year. Which day is that? Think about that for a little bit. Back to the diagram here. When we look at daily temperature variability, we'll see starting at midnight, the temperature declines. It decreases until about 6 a.m., until about the time the sun rises. That's generally the minimum daily temperature. Once the sun comes up, the temperature begins to rise. The sun reaches its maximum at high noon, 12 o'clock. But the temperature continues to rise beyond that time. The temperature maximum is usually around a little bit before 4 o'clock to a little bit after 4 p.m. And at that time, there's a balance between incoming radiation and outgoing radiation. Now, all day long as the sun's been up, the Earth has been acting like a black body. It's been absorbing all incoming radiation, it's been converting it to a longer wavelength, and it's re-emitting it to space. So the Earth is essentially storing up energy at the surface here and radiating it at the same time. It's going to reach a maximum, again, right about here. And at that time of maximum between incoming and outgoing, when it's balanced, we're going to reach a maximum temperature. Again, this is going to happen every day. And this is why the temperature isn't highest at noon. And as we'll see, it's also in a kind of similar way why the maximum summer temperature is not June 21st when insolation is at its maximum in the northern hemisphere, for instance. If we look at diurnal temperature variation during any given day in July for the United States, what you'll see is that here in the western U.S., we tend to have higher diurnal temperature variability during any given day. What's the difference between this portion of the United States, the Great Basin, the Snake River Plain, eastern Oregon, easternmost California, Utah, southern Wyoming, etc.? What is it about these areas that differs from these areas other than the mountains? One of the things you'll notice right away if you're to visit one of these areas is it's very dry. This low humidity allows for greater diurnal temperature variability, as opposed to here in the Midwestern U.S., where humidity is high and diurnal variation is low. So humidity is playing a role here in the temperature variability. The higher the humidity, the longer it takes to warm up the atmosphere and the longer it takes to cool off that atmosphere. During any given day, the temperature doesn't rise as much and the temperature doesn't fall as much in the following night, as opposed to in arid regions in the West, where we get very high temperatures in the daytime. Just a few weeks ago, we had a temperature here in Southern California and the Nevada border that I believe was 54 degrees centigrade, about 131 degrees Fahrenheit, close to the record highest temperature ever observed on the surface of the Earth, just a few degrees short. A very high temperature in the daytime, and if any of you have ever been to a desert, gone camping, you'll know that it gets cold at night. So we could have temperatures in the 50s centigrade in the daytime, and temperatures maybe close to zero or even below zero at night. Now, when we talk about atmospheric circulation, the first thing we'll consider is the movement of the wind. This is horizontal for the most part, and it's due to differences in pressure from one location to another at the Earth's surface. Air will move over an object, it'll move vertically over that object if it's pushed for some reason. And this is often the case with mountain ranges. Or it'll move over something if it's more buoyant than the surrounding air. It can move over another air mass, for instance. If one air mass is more buoyant than another and they collide, the more buoyant one will rise up over the less buoyant one. And that's a meteorological term we would call an occluded front, where a mass of air is lifted by some opposing air masses. Buoyancy of an air mass is controlled by differences in density. These differences in density are usually the result of differences in temperature and moisture content between air masses. Different air masses have different temperatures, and they have different moisture contents, different humidities. This results in different physical characteristics of those air masses. Vertical air movement is when an air mass rises because it's less dense than the surrounding air. You can think of this as a bubble or a blob of molten paraffin in a lava lamp, or a Remax balloon rising over the prairies here in Saskatchewan. If an air mass becomes less dense because it's heated, or if it becomes less dense because of more moisture, it's going to rise. If we heat air, the reason it becomes less dense is because the air molecules are more excited. They're vibrating and rotating at higher rates, and this forces them to take up more space, essentially. They're punching outward. They're keeping a greater social distance between other molecules in a mass of air. So by spreading these molecules out, we reduce the density, and the net result is usually a rising air mass. Moisture does something similar, but in this case, it doesn't spread the molecules out. It just intersperses the molecules with water molecules. In this case, the air molecules are mostly nitrogen, about 80%, about 20% oxygen. Realistically, 79% nitrogen, 20% oxygen or so. If we squeeze some water molecules in there, they have a lower mass than the nitrogen molecules or the oxygen molecules. Why is that? We have to go back to molecular weight. The molecular weight of an oxygen molecule is 32, usually. The molecular weight of a nitrogen molecule is 28, usually. And we'll see why I say usually later on. The net result is the air molecules weigh 32 atomic mass units, 32 daltons, or 28 daltons. A water molecule weighs 18 daltons. Well, nitrogen molecules consist of 2 nitrogen atoms, usually weighing 14. Oxygen molecules consist of 2 oxygen atoms, usually weighing 16. A water molecule consists of an oxygen atom that weighs 16 and 2 hydrogen atoms that weigh 1. The net result is 18. The atomic mass of a water molecule being much, much less than nitrogen or oxygen means that adding those water molecules to a body of air is much like adding helium or hydrogen to that volume of air. It makes the resultant air lighter. And if it was pumped into a balloon, it might be light enough that it'll rise above the surrounding air mass. What drives the horizontal movement of air? Basically, in the most basic terms, it's air flowing from higher pressure regions to lower pressure regions, or areas. The greater the difference in pressures, the stronger the force. The distance between the area of high pressure and the area of low pressure also determines how fast the moving air is accelerated. Now, meteorologists refer to this force that starts the wind moving or flowing as the pressure gradient force. In this case, high and low pressure are relative. It's not the exact number of the high pressure system or the exact number of the low pressure system. It's the difference between the two. And here we have an example in standard units. Unfortunately, high pressure is at 15 pounds per square inch. The low pressure system, located 500 miles away, is 14.5 pounds per square inch pressure. This results in an 80 mile an hour wind developing in a period of 3 hours. If we take these same pressure cells, 14.5 pounds per square inch, here's the low, 15 pounds per square inch as the high, and move them further apart, we're going to reduce the pressure gradient force considerably. In this case, we have an 80 mile an hour wind generated by these cells being 500 miles apart. We move them another 500 miles apart, and we end up with a 40 mile an hour wind. A very different dynamic. 40 mile an hour winds can do minor damage to unstable things, knock over tables and chairs, things like that. An 80 mile an hour wind can carry things away. That's when you see flying trampolines and dumpsters. And when we look at a weather map, one of the things that may not usually get your attention, hopefully it will from now on, are the H's and the L's. H stands for a high pressure cell. In this case, the pressure is going to decrease in all directions from the center. The highest pressure is right here where the H is. If you move away, the pressure gradient force is going to be reduced. The further away you get, the further the reduction. Air is always going to move away from the H in every direction. An L, on the other hand, depicted down here, is a low pressure cell, and it's the geographic center of that low pressure cell. In this case, the low pressure cell is going to result in air coming from all directions, streaming towards this L. because there's a relative lack of air here. Again, relative. It's not really a lack of air. It's a relative reduction in the amount or density of the air here. So it's being replaced. Here, the air is high pressure. It's going to move away from that high pressure, equalize eventually. Contour lines that you see on a weather map are called isobars. These isobars mean lines of constant air pressure. Bar meaning pressure, iso meaning the same. If you travel along one of those isobars, the air pressure that you would experience would not change. And again, from the last diagram and from a bit of this diagram, the strength of the resultant wind is proportional to the isobar spacing. The closer the spacing, the stronger the pressure gradient force. Therefore, the stronger the winds. When you see really tightly spaced isobars on a weather map, you can be sure that there are very strong winds associated at that place on the Earth's surface.